Hey everybody, and welcome back to the Toddler Whiteboard. Today we're going to do some more radical functions and we're going to solve some radical equations as well. So just real quick to kind of pick up where we left off last time, we had taken a look at kind of our basic radical functions. We looked at the square root function and we looked at the cube root function. And we had kind of a basic idea of the shapes of these graphs. The square root function looks something like that, and then the cube root function looks something like that, going through the origin right there. And we said, for this graph, the domain is only from 0 to infinity, so 0 and then any positive numbers, and then the range was the same, 0 up to infinity. And then for the cube root, it was a little different. You had the domain being all real numbers because you could take the cubed root of a negative number, no problem there. And the same thing for the range because it'll go up and down forever. So let's take a quick look at some higher order radical functions and just kind of see how they compare. So let's move up to like the fourth root and the fifth root function. And you're going to start to kind of notice a pattern here, so it's actually pretty nice. So if you take a look at the fourth root function, you'll notice that the fourth root has the same problem that the square root has. That is, if you try to take the fourth root of like a negative number, you're going to run into problems. Because this is asking what number should you multiply by itself 4 times in order to get negative 16. And we know that if you multiply an even number of things together, it always has to be positive, right? Because if this were negative numbers, for example, negative 2 times negative 2 is 4, negative 2 times negative 2 is 4, so you're going to get a positive 16, not a negative 16. So it turns out that the fourth root function is going to have the same restriction that the square root function did. In fact, this will happen for all of our even roots. So this one's going to have a domain where you can't have negative inputs, so we're going to start with 0 and go from there. And the same thing's going to happen with our range. We're only going to be able to get outputs that are 0 or higher. And if you take a look at this graph, you'll actually see it looks really similar to the square root graph, but it's going to be a bit flatter and a bit steeper right here at the start. So let me show you kind of a better rendition. So we'll take a look at the actual graph. Hopefully you can see this okay. So that's the fourth root function right there. And then I'm going to compare it to the square root function. So the square root function is in green. And you can see how the fourth root function, the blue one, is actually a bit flatter. And it's a little bit steeper right here around the origin. But they have a very similar shape. So we'll see that that's kind of the pattern for all of these even roots, is they all have that similar shape as the square root function. Okay, there's the square root, and then there's the fourth root. All right. So the odd roots also have a pattern, because again, like if you're dealing with the odd root, you have the same issue as like the cubed root, where you don't really have problems with the negative numbers. So like if you take the cubed root of negative 32, for example, that's totally fine, because if you do negative 2 times negative 2 5 times, these are going to become positive, these are going to become positive. When you have an odd number of things you're multiplying, you always have one guy left over. And in this case, this last one's going to be negative, so we'll have a bunch of positives and then a negative. So when we multiply this out, we'll actually get negative 32. So for the odd roots, there's no problem with the domain. You can throw anything in there. So the domain for this is going to be negative infinity to positive infinity, and the range is going to be the same, just like for the cube root. So when you take a look at this graph, it's going to look really similar to the cube root graph. Again, it's going to be a little more flat, and it's going to be a little steeper right here. Actually, I should probably draw this more like that. It's going to be pretty steep. In fact, like right in the origin, those like the cube root and the other graphs get vertical essentially. They don't actually become vertical because that would fail the vertical line test, but If you go into like a calculus class, you'll kind of see that right there in the middle, they get really, really close to vertical. They get close to the origin. All right, so let's take a look at this one on the computer so you can get a better idea of how the fifth root looks versus the cube root. So, all right, so this is the cube root right here, the orange line, and then I'm going to lay the fifth root on top of it right there. So the fifth root is the gray line. You can see that the gray line's a bit flatter. It doesn't grow quite as fast, and it's pretty, you know, the middle of the graph gets pretty close to vertical. Like you could zoom in and you can see that it's not exactly vertical, but we say that the derivative, again, if you take some more advanced math classes, we say that you'll find that the derivative actually doesn't exist there because, well, we don't have to get into that, but just know that it gets pretty steep right there, right in the middle. Okay. So it turns out that all of the even roots are gonna kind of look the same. Like this is the sixth root one right here. Oops, let me turn it on. So that's the sixth root of x. It looks even flatter and then steeper in the middle than the fourth root. And then I can do the eighth root also. Let me put that in here. I'm just typing them as into the 1/8 power in here to the 1/7 power. This is GeoGebra, so you know you can try this GeoGebra on your own computer. So that's the eighth root function. So you'll notice that that's a pattern with these functions. Is that anytime you have an even root, you know, if you have something like this, an even root of x versus an odd root of x, the even roots are always going to have like this similar, you know, this basic shape. There's going to be some variations on it, but it has like that basic shape of the square root graph, and then the odd ones are going to have the same basic shape as the cube root, and they're just going to change kind of in how steep they are and how flat they are as they extend out. Okay, so they're actually pretty nice. So if you're ever dealing with an odd root function, you automatically know that the domain is going to be all real numbers. And then if you're dealing with the even root function, it's going to have a restricted domain, so you have to figure that out. Now, you have to be a little bit careful here because it's not always going to be 0 to infinity. So, for example, if you were dealing with something like this, I'm going to use black. Make sure it shows up. Say you were dealing with like the fourth root of 3x plus 2, and you're trying to figure out what the domain is of this. Well, for this class, you know, what we need to do, there's two ways we can do it. We can graph it and kind of see what the domain looks like. Like if we want to figure out we can figure out the horizontal intercept pretty easily. We just set the output equal to 0, and then it's the fourth root of this. And then to undo that fourth root, I'm going to take both sides as a power of 4. And again, the 0 is going to stay 0, so that's pretty nice. And then the fourth, taking the side to the fourth power undoes the fourth root, so we just end up with 3x plus 2. So I'm going to have negative 2/3 is going to be my horizontal intercept. And then you can kind of take a look at it and see the vertical intercept is going to be a positive number. Or it is going to exist, I should say. It's going to be the fourth root of 2, because if you put in x equals 0 right here, you're going to get the fourth root of 2, which I don't know what that is off the top of my head, but it's some positive number smaller than 1. And so, or I'm sorry, a little bit bigger than 1, I should say. And then we have that this is going to be, like right here is going to be the negative 2/3, 0. And then we're going to have our root. I can like get an approximation real quick on my calculator. Let's see what 2 to the 1/4 power is. Yeah, 1.19 approximately. So that's going to be about right here. You know, so we're going to get something that looks like that. So you can see pretty easily here that the domain is going to be from negative 2/3 up to infinity. If you wanted to do it algebraically, the way that we did last time, what was it? It was 3x plus 2, I think. I erased it without remembering it. 3x plus 2. If you want to do it algebraically, what you can do is, since it's an even root, you know that anything under the even root has to be 0 or greater. So you can just take this guy out and force it to be greater than or equal to 0, and then solve it from there. So subtract the 2, so you get 3x is greater than or equal to -2, and then divide by 3. X is greater than or equal to -2/3. You only reverse the sign if you divide by a negative number, so we're dividing by positive, so no problem here. So that'll give it to you automatically, algebraically. You can use the graph as well for this class to take a look at it. If you take like the next algebra class, you'll probably want to do more algebraic work just to ensure that, because we can get some graphs that look a little bit different. We can make some graphs that go up and down as well as moving left to right. All right, cool. Let's take a look at solving some equations. So we've been solving some radical equations where we have it equal to 0, like when we're trying to find the horizontal intercepts. And I told you it was good to go ahead and learn like that process of like taking the powers of both sides, even though we always end up getting a 0 on one side, because now I can apply this to like a more complicated problem. So I can do something like this, for example. So I'm trying to solve this equation. I'm trying to figure out which x value, if I put it in here and then multiply it by 3 and then add 2 and then take the square root, what number is going to give me 9? So the nice thing is we can use the exact same method that we've used before to solve this. So the idea is we need to get the x out of here, but to do that we have to get rid of the root, the square root. So I need to undo the radicals. So to undo the square root I can take it to the second power. But again, I have to do that on the right hand side as well. So this squaring is going to undo the square root, so on the left hand side I'm going to end up with 3x plus 2 is equal to 81. Now this should make sense because we said that the square root of 3x plus 2 is equal to 9. So that means whatever was under the square root, it better be equal to 81, because when you take the square root it's got to equal to 9. So it makes sense that the 3x plus 2 has to be equal to 81, because when we take a square root here we get 9. So again, it's not really magic, we're just kind of following these logical steps. Alright, now I just got a simple two-step equation, subtract 2, divide by 3. So I'm going to get that this is 79 over 3. Now, the tricky thing about these is you have to check your answer, and I don't mean that in a sense of like you should check your answer like you should always do with an equation. I mean you have to check the answer because it's possible to get what we call extraneous solutions. Okay, that's kind of a big word that just means fake solutions. Okay, in other words, we can get solutions that don't actually work in the equation. I'll show you an example of why that happens here in a second. All right, so I have to check this, and again, this is not optional. You need to always check your answer for these. So the square root of 3 times 79 over 3 plus 2, is that equal to 9? Question mark. 3 times 79 over 3 is going to be 79. So I got square root of 79 plus 2, is that equal to 9? 79 plus 2 is 81. Sure. That's equal to 9. So we know that's a good answer. So we can keep that answer. All right, let me show you why you have to check it, why you can get an extraneous solution. The reason this happens, actually let me close this door real quick. The reason this happens is because if you go around squaring sides of an equation, you could possibly take things that used to be negative and you can make them positive, which will give you like a false answer. So for example, if you had something like this, all right, square root of 2x plus 1 is equal to -3. Now, if you're clever, you'll realize that this can't have a solution, because if you ever take the square root of something, it has to be 0 or higher. You'll never get a negative answer out of a square root. So you know that this can't have a solution, but let's say you don't see that, you're just kind of plowing through and doing the algorithm. So what happens is you square both sides. So by the way, we knew this original statement had to be false, because if you take the square root, you'll never get a negative number. But after you square this thing, when you square the -3, it turns to a positive number. And so now all of a sudden we've taken something that was there was negative and now it's turned positive, that actually would be okay in this sense. That would be an okay statement. But we're going to see that when we try to solve this, it's actually not going to work out. We'll get an answer, right? I'll subtract 1 and get 8, and then divide by 2 and get x equals 4. So that looks like an answer, but when I go over here to check it, that's when I'm going to catch it. I'm going to get the square root of 2 times 4 plus 1. Is that equal to negative 3? So that's going to be the square root of 8 plus 1, so the square root of 9. And this is not true. The square root of 9 is not equal to negative 3, it's equal to positive 3. And so that tells us that this is an extraneous solution, so this one actually has no solution. So this is why we have to always check. It is possible to get these extraneous solutions. In this course, we're not going to have a ton of them, but you might have a couple pop up. If you make these a little more complicated, it's more common that you'll get some extraneous solutions. If you make some more, you can make these equations a bit bigger with the radicals in them, especially if you have multiple radicals. You could have like 2 different square roots in the equation, and then you might end up with a couple, like an extraneous solution pretty easily. Okay, let's try another one here. So how about if you have a number in the front, so something like this. Alright, so let's try one like this that has a number in the front here. So what we're going to do is we're going to realize that this is 3 times the square root of 4x minus 2, and if we do that, we can actually solve this really easily. There's actually 2 ways to do this. I'll show you what I think is the easiest way first, and then maybe I'll show you the other way as well. So since this is 3 times this root, what I'm going to do is I'm actually going to go through and divide both sides by 3. That's okay because this is multiplication. It's the same thing you would do if you had like 3x is equal to 12, 3 times x is equal to 12, so you can undo the multiplication by doing division. So that's okay. But again, it's the fact that this is multiplication here. And that's going to make things a lot easier because now I'm going to have the square root of 4x minus 2 is equal to 4. And now I'm going to just square both sides like I did before to get rid of the square root. So square, square, and then I have 4x minus 2, because the square undoes the square root, is equal to 16. Add 2 to both sides to get the 4x is equal to 18. Alright, so now we divide both sides by 4. We're going to get 18 over 4, and that's 9 over 2. So again, let's go over here and check it. 3 times the square root of 4 times 9 over 2 minus 2, is that equal to 12, question mark. So 4 times 9 over 2, that's going to be 18, and then subtract 2, that's equal to 12. So 3 times the square root is 16, is that equal to 12? So 3 times 4 is equal to 12. Yeah, that's good. So this is a good answer right here, 9 over 2. But again, we have to check it just to make sure that we don't have, some kind of extraneous solution. All right, let me do maybe one more of the square roots, and then I'll show you 1 or 2 of the different roots. All right, so here's another kind that you might see. You might see something with like addition in it. So we could have something like 2 times the square root of 3x plus 2 is equal to, let's do addition right here, plus 4 is equal to 16. Alright, so just like we have this 2 out here, we also have this plus 4 out here that we want to get rid of. Think about like an equation. If you had like 2x plus 4 is equal to 16, think about what's the first thing you would do. You wouldn't do division by 2 first, you would do the subtraction of 4 first. You would subtract 4 and then you would divide by 2. So the same thing right here, you can kind of think of this as like the big variable right here. So we want to subtract the 4 and then divide by 2. So I'll start by subtracting the 4 first. So let's see, I'll get 2 times 3x plus 2 is equal to 12. Now I'll divide both sides by 2 to get the 2 to go away. And so now I have the square root of 3x plus 2 is equal to 6. Now I'm at a spot where I can just square both sides. Like this. And then I get 3x plus 2 is equal to 36. Subtract 2 from both sides. 3x is going to equal to 35. So x will be equal to 35 over 3. Okay, so hopefully this checks out. Let me do a quick check over here. If not, maybe we made a mistake. See, 2 times the square root of 3 times 35 over 3 plus 2, and then all of that plus 4, is that equal to 16? So 3 times 35 over 3 is 35. Let's see, did I make, oh, you know what, I made a mistake right here. This should be 34. This should be 34, so it should be 34 over 3, not 35 over 3. And actually it's good I checked it because I caught my mistake. So 34 over 3, 34 over 3 times 3 is going to be 34 plus 2. So I'm going to get 2 times the square root of 36 plus 4 is equal to 16. Square root of 36 is 6, so this is 2 times 6 plus 4, and yeah, that's equal to 16. 2 times 6 is 12 plus 4 is 16, so this is a good answer, right? Alright, so hopefully you're starting to get the hang of these. It's just like solving equations, but what you want to do in general, the strategy is that you want to isolate the radical first, get the radical by itself on one side of the equation, and then take both sides to a power. That's kind of our general strategy for all of these. So do whatever you need to, subtract, divide, to get that radical by itself, then take both sides to a power. Alright, let's do one that's a little bit different. Alright, so let's take a look at one more that's a little bit different. Let's take a look at something like this. Okay, so the square root of 4x is equal to x minus 3. Now in this one, we have the radical isolated already, so there's nothing really to do. So I can go ahead and square this. What I have to do is be very careful on the right-hand side. This is not x squared minus 3 squared. This is actually going to be x minus 3 times x minus 3. So I've got the square root of 4x. When I square that, the square root goes away, so I'm just end up with 4x. So that's no problem. But on the right-hand side, I have to actually multiply this out. So this is going to be x squared minus 6x plus 9. Now if you notice what happens is when we do this, now we have a quadratic equation. And that happened because we had an x here and we also had an x over here. That when we squared it, we ended up with an x squared. So now I have a quadratic equation to solve, and the way we solve quadratic equations is we have to get them equal to 0. So it's going to be easiest to move everything over to the right-hand side, and then we're going to either try to factor it. If it doesn't factor, we can always throw it into the quadratic equation. So hopefully it'll factor really easily. So all the stuff from the previous chapters on factoring, it's not going away. You got to make sure that you keep those skills up. All right, so we're going to subtract 4x over here, so I get a 0 on the left. And then minus 10x, negative 6x minus 4x. Again, I'm just kind of subtracting this if you're not sure what I'm doing. Minus 4x, and then plus 9. So hopefully this thing factors. So I'm looking for two numbers that when you multiply them, you get positive 9. When you add them, you get negative 10. Those numbers are going to be minus 9, minus 1. Okay, so that's your factor for us. So this is going to give me two answers, x equals 9 and x equals 1. This is back from chapter 6. It's solving those equations. We're actually using that within these radical equations. All right, now I do have to check both of these just to make sure that they work in the original equation. So let's see, if I put 9 into here, I have to put the 9 here, and I also have to put the 9 here. So the square root of 4 times 9, is that equal to 9 minus 3? I'm checking back in the original equation before I did any squaring, okay? So you have to make sure you do that. So the square root of 36 is equal to 6. Sure, that's true, so that's good. Now we gotta check the 1. The square root of 4 times 1, is that equal to 1 minus 3, back in the original equation? Alright, so let's check that out. So this is the square root of 4, is that equal to negative 2? Actually, that's not true, right? Square root of 4 is equal to positive 2, not negative 2. So this is a false answer right here. That's an extraneous solution. So what we do is we come down here and say, you know what? 1 was an extraneous solution. 9 is the only solution that I'm going to get from this one. We're not going to have two solutions in this particular case. All right, so that's an example where you might get an extra solution that pops out that doesn't actually work in the equation. All right, so there you go, a nice example of an extraneous solution that you get from having to solve a quadratic. So everything's kind of coming together. You can't forget your factoring stuff, your quadratic formula, all that stuff you're going to have to keep using in this chapter and in the next chapter. So if you feel like you didn't do so great on that in the last chapter, make sure that you're going back and relearning that material. All right, let's do one or two with some cubed roots or some fourth roots or some other powers just to make sure we know how to do them. And then I think we'll call it a day. So how about something like, I'm pulling some from the back of the book here, or maybe I can make some up. How about the cubed root of 3x plus 1 minus 2 is equal to 5. Okay. Let's make the numbers a little smaller. Let's make this a 1. All right, so the same idea that I had before. I need to isolate the radical and then take both sides to the power to make the radical go away. But isolating the radical is step number 1. So you got to think kind of what would you do if you had x minus 2 is equal to 1. You can kind of think of this thing as just a big variable for the moment. You're going to add 2 to both sides. So that's what I'm going to start doing right here. Add 2 to both sides of this equation. I'm going to get cubed root of 3x plus 1 is equal to 3. Now to undo the cubed root, we don't square, we take it to the third power. Cubing and taking the cube root are the inverses of each other. So we'll cube this side, cube this side. The cube and the cube root knock each other out. 3 cubed is 27. Okay, 3 times 3 is 9, times 3 again is 27. Now again, same process. I've got a 2-step equation. Subtract 1 from both sides, divide by 3. So I'll get 26 over 3. So it's really the exact same process as dealing with the square roots. It's just when you get to the power part, you have to take the power that's the inverse of whatever root you're dealing with. So it's actually exactly the same. And then of course we have to check our answer. The cube roots aren't going to usually give you problems because the domain is infinite, is from negative infinity to positive infinity. But you should still check your work just to make sure. I can do a quick check of this one. The cubed root of 3 times 26 over 3 plus 1 minus 2, is that equal to 1? Alright, so this will be 3 times 26 over 3 is 26, so the cubed root of 26 plus 1 minus 2 equal to 1. Cubed root of 27 minus 2, is that equal to 1? So this will be 3 minus 2, yeah, that's equal to 1. So there we go, that one works out fine. Maybe I'll do one more quick one that has like a fourth root in it. So let's do one like this. How about 2 fourth roots of x plus 3 plus 6 is equal to 2. All right, so we'll get a nice big one. 2 times the fourth root of x plus 3 is plus 6 is equal to 2. Now again, make sure when you're putting that 4, you're putting it up in the radical. You're not putting it out in the front, so it's not 4 times that. This whole thing, the fourth root, is like one big symbol, so make sure you write it like that. All right, again, if you're thinking about what to do, think about what you would do if you had this set up right here, right? Just kind of think of this as one big variable to start. We want to get this thing by itself and then take both sides to the power. So the first things first is to get this thing by itself. So if you had 2x plus 6 is equal to 2, you would subtract 6 and then divide by 2. All right, so let's subtract 6 from both sides. And then we're going to divide by 2. All right, so I'm going to get the fourth root of x plus 3 is equal to negative 2. Now at this point, if you're good at these, you'll realize that this actually is going to lead us to no solution. Because if you take the fourth root, the range of the fourth root function is only 0 and positive numbers. So there's no way you're going to get a negative number out of the fourth root. Now, if you recognize that, great. You can stop here and say that there's no solution. But let's say you don't recognize that and you keep going. All right, so the process would be that since this is a fourth root and it's isolated, we want to take it to the fourth power. That's going to undo the fourth root. And then we're going to take the right side to the fourth power also. All right, so fourth root to the fourth power goes away, so I get x plus 3, and then negative 2 to the fourth power is 16. So I'm going to get 13 for my answer. Now, you got an answer, but that doesn't mean that the answer works. We have to check it. All right, so let's go back up here and check it in the original equation, see if it works. We know that it's not going to, but again, if you're doing on an exam or something, you didn't catch it, this is how you catch it. All right, so 2 times the fourth root of 13 plus 3 plus 6 is equal to 2, question mark. 2 times the fourth root of 16 plus 6, is that equal to 2? The fourth root of 16 is 2, so this is 2 times 2 plus 6 is equal to 2. This is 4 plus 6 equals 2. In other words, that's saying that 10 is equal to 2. Obviously, 10 does not equal to 2, and that tells you that this guy right here is an extraneous solution. Now, you have to be a little careful. If you go through and you work it out and you don't get a true answer, that could mean it's either extraneous solution, but it could also mean that you made a mistake when you went through and originally solved the problem. So you should do two things. You should, when you check your work, if you get like a false solution here, you should actually go back and check your algebra first to make sure you didn't make an algebra mistake anywhere. Because if you make an algebra mistake, you might have just gotten the wrong answer. If it doesn't look like you got the wrong answer, you can go through and probably assume that it's an extraneous solution. If you really want to check, you could graph both sides of the function like we do with the intersect method. And then you can see if they don't intersect, then you're not going to have a solution. But if they do intersect, that means that you just made an algebra mistake somewhere. All right, guys, hopefully that's helpful. I'll catch you next time, and we'll move into the rational functions, I believe.